Saad asked how to do homework problem number 7. This is the astronaut problem. It says an astronaut in her spacesuit has a total mass of m1, including the suit and oxygen tank. So m1 is the astronaut's mass plus the tank's mass. Her tether line loses its attachment to her spacecraft while she's on a spacewalk. Initially at rest, so the initial speed is going to be 0. She throws her oxygen tank, and they give you the mass of the oxygen tank. With the speed that's also given. And the reason why she does that is because that's the only way she can move. When you're in space, there's nothing to push against. There's no ground to push against with friction or a normal force. So if you want to move, you have to do some kind of rocket-like motion. You need to expel some mass so that you can push against it and have the Newton's third law reaction force of that object pushing back on you. So the astronaut is floating around in space, separated from her spacecraft. The only thing she can throw is her oxygen tank, which means she better throw it fast enough she can make it back to the spacecraft in the amount of time she can hold her breath or with the remaining air she's got left. So that delta T is the amount of time she has left to breathe. That's also given in the problem. Okay, let's set this problem up using conservation of momentum. The initial state will be the astronaut just motionless in space, and the final state will be after she throws the oxygen tank and things are moving. So the initial momentum is m1 times the initial velocity, which is going to be 0. So the left-hand side of this equation will be 0. And then after the throw, you have the astronaut with her own momentum, and the oxygen tank with its own momentum. So the left-hand side of this is 0 because the astronaut's motionless to begin with. Now she throws the tank, it's got some velocity, so that means the astronaut can have some velocity too. So we have MAVA equals minus M2V. Since this is kind of a one-dimensional problem, we don't need to use the vector signs for the rest of it. The plus and minus signs will do the trick. And keep in mind that the astronaut's mass is m1, that total mass, minus the mass of the tank. So this is really m1 minus m2. And I'll just write VA without the vector arrow on top. V with no vector arrow. So now we can see that the astronaut's velocity after this throw is m2 over m1 minus m2 times the velocity of the tank. Okay, so that's how the astronaut's able to move. Now, she's got to make it back to the spacecraft before she runs out of air to breathe. And the distance traveled is going to be the astronaut's velocity times time. So we'll see what that value of distance traveled is and whether it is sufficient for the astronaut to make it back to the spacecraft. So this problem it's kind of conceptually interesting because it shows you the only way to move is to have something to push against. This is true no matter where you are. If you're on the surface of the earth and you want to move, you want to start walking, the reason why you're able to walk is because there's friction between your foot and the ground, and you apply a friction force that way on the ground, and by Newton's third law, the ground applies a force of equal magnitude in opposite direction on your feet, so that you are able to move forward. Now in space, there's no ground or earth to push against, so you have to have some other object to push against, and the astronaut made the tough call of pushing against her oxygen tank.